Good afternoon, everyone. Thank you for joining. My name is Feras Saad. I'm a PhD student at MIT working with Vikash Mansinga, and my co-authors are Cameron Frey and Martin Renard. We're talking today about optimally sampling from discrete probability distributions. And all the work in this slide is available on GitHub for those who are interested in using the algorithms presented here. So first, we'll give an introduction and give some motivation for the talk. We'll give an overview of our approach and describe experimental results and related work. And then there's a technical appendix for those who might be interested in that takes some of the technical content in the paper and makes it a little bit more digestible. So first of all, what is a random sampling algorithm? And throughout this talk, we'll assume that we have some probability distribution P, which is comprised of rational numbers between 0 and 1. And so a sampling algorithm is any randomized algorithm which returns an integer j with a specified probability pj. And here we are focusing on the fact that these are rational probabilities. Now, for those of you who work in computation, you might know that sampling is a very fundamental operation to many, many fields. It arises in artificial intelligence, robotics, operations research, and general scientific computing as an enabler for many of the Monte Carlo algorithms that appear and arise in these applications. And so toward this end, many libraries provide algorithms for sampling from discrete probability distributions. So the interfaces are roughly the user specifies a list of weights or a list of probabilities, and the system returns an integer according to those weights. And these arise in MATLAB and C++ and R. So now let's look at some of the issues with these samplers, which I'm calling floating point samplers. In specific, floating point samplers are typically the samplers that are implemented in the common libraries. So these libraries assume roughly that the sampler, A, has access to an entropy source that's emitting this perfectly uniform random number, which we're calling U, and it then transforms this uniform random variable into a sample from the discrete probability distribution. And these assumptions are laid out in a classical textbook on random variate generation by Luc Devroy. And roughly the assumptions are our computer can operate with real numbers, there's a perfect generator for uniform random variables, and all the operations such as addition and division and subtraction take unit time. So this is called the real RAM model of computation. And so statisticians love this model because they can prove very sophisticated theorems about transforming this infinitely precise random variable U, assuming that all they have is a real RAM. And then library developers or computer scientists take these mathematical algorithms and transcribe them very easily onto a computer. And in practice, they're using these floating point approximations to the real RAM machine. Now, one of the shortcomings of this model is that it abstracts away details of entropy resources, numerical precision, computability, complexity. And this is important for both practice and theory. So in a classic paper from 1951, von Neumann criticizes very sharply this practice of generating random numbers using analytic or arithmetic models, saying that it's sinful, it's imprecise and obscure because there's imperfectly understood behaviors of round-off errors, and that essentially we can prove nothing about these algorithms because of their fundamentally questionable assumptions, and that it's very silly to even talk about taking uniform random numbers and putting them through logs and exp, etc. So let's try and understand a little bit what von Neumann means in his criticisms. So here we have a discrete probability distribution, P1 through Pn. The universal algorithm to sample from this is that I align the probabilities into bins in the unit interval, and I'm going to throw a dart. And then depending where the dart lands, I'm going to return the bin that dart fell in. So roughly we simulate a uniform number in the interval, and we return the bin that it falls in. It's immediate to see that this is a correct algorithm. So there are at least two sources of error that arise when we implement this in C++, for example. One is actually computing the running sums, and the second one is actually getting this perfect uniform random variable U. So let's look at the C++ standard library. The interface roughly is that the user specifies a list of non-negative numbers, which are the weights, which they're calling W0 through Wn-1, and the guarantee is that it returns an integer according to those weights. So in this example, I wrote a little C++ program where I'm specifying 1, 2, 1, 3, 5. So I want the probabilities to be as they're shown on the slide. But in practice, the probabilities that I'm sampling from are non-exact. They're these double precision floats. And the second issue is that we need this uniform random number, this perfect uniform random number. And the way that this is generated in C++ is that they generate this 64-bit random word and divide it by 2 to the 64. And the user gets to specify how much precision that this uniform random number uses. And then there's also, aside from these two sources of error, a fundamental inefficiency. So in C++, they use roughly 53 bits of precision to generate a uniform random number. But you can take a very simple example to see why this is inefficient. If all I want is a fair coin flip, and I generate 53 random bits, I've wasted 52 of them because all I need is one random bit, rather than generating this full machine word. So in summary, these samplers, they waste random bits, and they have suboptimal sampling errors. And the waste from random bits comes from generating full machine words. And actually, in practice, what we're going to show in this talk is that this does lead to slower wall clock time, because calling the random number generator is a very fundamental sort of operation that happens. And we can design fast samplers that lead to 100 to 10,000 times speedups over standard implementations. So this is important in practice. The second component of having suboptimal sampling errors, you might say, okay, these are 53-bit mantissa, so they're tiny, but actually if you generate hundreds of millions or billions of simulations, which common samplers today can do, these errors magnify. And so later in this talk, we're going to show that the samplers we develop can be 100 to 10,000 times X more accurate than standard, on standard probability distributions than existing sampling algorithms. Okay, so now let's look into our proposed approach. What we're going to do is we're going to design samplers for discrete probability distributions that are optimally efficient in their use of random bits. They only draw as many random bits that are theoretically needed for that distribution, and that they're optimally accurate, because we're operating in this limited precision setting, so that there's this question of if you fix the precision, you're going to have some sampling error. And so we want the most optimal algorithm for that. The main contributions of this paper are we precisely formulate this problem and give algorithms for finding optimal algorithms. We show how to construct these samplers, and we compare them to limited precision algorithms both for exact and approximate sampling. And we show that these enable trade-offs where existing algorithms don't quite enable those trade-offs. So these are our goals. Let's look into the first goal. The idea is that rather than generate a uniform random variable, u, all at once, we're going to just randomly generate these random bits and use them as the basis for our sampler, extending an idea by Knuth and Yau. So rather than this analytic model of sampling, Knuth and Yau in 76 devised what's known as the random bit model of sampling, which is roughly saying that the sampler is an algorithm that takes this lazily generated stream of bits and converts it into a sampler. So in comparison to what we saw earlier, rather than have this infinitely precise random variate, we're just calling this primitive called flip, and that's giving us the bits, and then our sampler is consuming those bits. So this is a much more computable setting. What's very nice about this random bit model is we can represent any probabilistic sampler as a tree. And so this is a decision tree, basically, and its semantics are you start at the root, and you flip a coin. So if it's 0, you go left. If it's 1, you go right. And then if you reach a leaf, then you just return the outcome of the leaf. Otherwise, you call another coin. And so this is called a discrete distribution generating tree. And so here what I'm showing is a tree for rolling a coin. So roughly you start at the root. If you get 0, you go left. If you get 1, you go right. If you get 0, you go left. And then you return 5. And so any sampler in this model is actually represented as a tree, the class of all algorithms. And so the key theorem of Knuth and Yau is they find the tree with the shortest depth for any specific distribution, and that's known as an entropy optimal tree, or a tree that most efficiently uses the random bits. And the key theorem is that these trees can be constructed directly from the binary expansions of the probabilities. So here, for example, I can take a probability distribution half, a quarter, write out the binary expansions, and then directly construct a tree by saying if the binary expansion of a specific probability is 1 at level j, then I'm going to put a leaf at that outcome, at that level. And then what I'm showing on the right is a tree which has the same distribution over leaves, but is entropy suboptimal because the average depth of a leaf is larger. And we can do this for rational probability distributions where we finitely encode repeating terms using back edges. That's fine. And then we can also do this for irrational probabilities, but obviously these are not computable. These are infinitely sized trees. So for the purposes of this talk, we're not really considering this setting. And Knuth and Yau, for those who might know some of these results, it's a very intuitive result, which says on average the amount of random bits you need to draw is given by the entropy of the distribution, plus or minus, plus at most two extra bits. So the intrinsic randomness in the target distribution is roughly as many bits as you need to draw, but there's this 2-bit cost that Knuth and Yau very smartly bound. So then the immediate question is, why don't we use this? Well, the unfortunate part of these exact entropy optimal samplers is they're exponentially large. So here on the x-axis, I'm showing the number of bits needed to encode the input distribution, the target distribution, and the y-axis on a log scale is the number of bits needed to encode the sampler. And since this is log linear, you can see it's an exponential growth. And so, for example, if I want to simulate from a very standard distribution like binomial, I'm going to need 10 to the 91 terabytes just to encode the Knuth-Yau tree. So completely impractical. And we formalize this in the paper where we show that you need only logarithmic space to encode the distribution, but you need much larger space, linear space to encode the tree. So log s to s is exponential. And Knuth and Yau heuristically observed this in their work where they said our algorithms are very complex and require a tremendous amount of space. So they're theoretically nice, but in practice not very useful. And so we want algorithms which extend the Knuth-Yau method. So what we're effectively going to do is we're going to establish an approach for taking these very large Knuth-Yau exact entropy optimal samplers, have the user specify a specific depth, what's the maximum amount of memory they want to consume, and then for that a specific amount of depth, find the most accurate sampler for a specific probability distribution. And this depth k corresponds to the precision. There's a formal matching between the depth of a tree and the precision allowed by a sampler. Okay, so now that we're cutting the tree, or we're truncating the tree, there's going to be approximation error. So the question is, what is the most accurate sampler we can get? And so now the problem is, for any distribution, find this tree, this sampler, with a pre-specified depth who has the closest approximation to the target distribution. And as we said, there's this correspondence between depth and precision, which is formalized in the paper. And here, when we say the tree has depth k, we're allowing for back edges. So these are like finite state machines, which represent the sampler's behavior. And so, right, this is the diagram which sort of should be in our minds, right? Which is, we specify depth, and we want the most accurate tree. And so the main result of the paper, which we'll go into a little bit, is that we show an algorithm which, given any probability distribution p, any specification of the bit precision of your machine, and any measure of statistical error that's given by an F divergence, we'll go into that later, we construct the most accurate sampling algorithm among all entropy optimal sampling algorithm given the specific precision. And a nice property of this is that it's provably more accurate than any floating point sampler out there, which draws k random bits and returns an outcome. And these are all the samplers that appear in MATLAB and NumPy and SciPy, etc. And so the F divergence, just to give you some intuition for what that is that it's sort of telling us how do we specify the error that we want to optimize over, the approximation error. So a divergence is anything that takes two distributions and returns a real number, which says a positive number, how far they are. And an F divergence is a specific divergence that's given by this form where it's the expectation of a convex function of the ratio of the probabilities. And these F divergences are widely used in probability and statistics. To give you some examples, there are the total variation distance that you might be familiar with, Pearson chi-squared, which shows up in statistical testing, KL divergence, or relative entropy in information theory. And so here we're just showing what are the generating functions, and these are all convex. And the convexity is going to be very, very important for our optimization approach. So the key insight in this paper is that, okay, we have this problem. We want the most accurate tree of a specified depth. One result in the paper is that we can actually describe any entropy optimal sampling tree as having output probabilities, which are all integer multiples of a specific number, 2 to the k minus 2 to the l for some value of l that's less than k. So roughly what this is saying in more precise terms is that optimizing over these samplers is really a balls to pin problem, where I have, say, 2 to the k balls, which represent how much what's the resolution my probabilities give me, and I need to assign them to n bins, which represent the probabilities my approximate sampler is going to assign to each different outcome. And so the question is that, we have this balls to bins problem, and it's a classic discrete optimization problem, but of course it's combinatorially large. And so one of the key algorithms in the paper is how do we solve this optimization problem efficiently, and we give an n log n solution for that in the paper, which is a greedy algorithm based on a smart initialization. So you start with a smart initialization of balls to bins, and then you just greedily move them around. That's the intuition. And it's n log n time, where n is the length of my target distribution. Okay, so we have a few more minutes left. Let's talk about why anyone cares about this. So we benchmarked our samplers against common samplers. One thing is that we get big speedups in comparison to standard samplers in the C++ library or other implementations of Knuth-Yau sampling in the literature. And these have both speedups in terms of the wall clock runtime, but also theoretical speedups in terms of the scalability of the approach. So we're the orange line over here, and we're showing the runtime versus the entropy of the target distribution. Another benefit is that because we're only calling the random number generator a variable number of times, as many times as needed by the target distribution, depending on how much entropy is in our target distribution, our sampler is going to call the PRNG a variable number of times. And this means that we're efficiently using the random bits. So our wall clock runtime is a function of how entropic the distribution is, in comparison to these samplers that call PRNGs a fixed number of times, and so that they run slower. They waste a lot of computation. Another sort of benefit of our approach is that these are also more accurate than standard samplers. So here what I'm showing are sort of cumulative errors of the relative error of approximate samplers from baselines to our approach. And these are 6 common families of probability distributions. And we're seeing that the relative approximation error can be 100 to 10,000x for standard distributions. And then one question is, we can use this to figure out how much precision we need for a given amount of error, depending on our error measure. So if you're using, for example, total variation, we can choose sort of how much precision we need for an optimal error, and this increases with the entropy. And then for different error measures, like the callback, the KL divergence, you actually need more precision. Error decreases with the entropy. So there's this flexible sort of set of decisions that we can make. And so a key punchline here is that when we're designing these samplers, different applications care about the error metric, and we're flexible in that approach. And then the final thing here is sort of just showing that we can roughly get the same amount of bits per sample as entropy optimal exact samplers, but we're using far less precision than exact sampling, and we're getting errors which are roughly tolerable, depending on how much precision you want. So an exact Knuth-Yau sampler will need enormous amount of memory, so we use less memory and we get very accurate samplers. And so just maybe for the last minute or so, or a few minutes, this shows up, or these applications show up in cryptography, where sampling from discrete distributions is a key subproblem for key generation, and they care about optimally sampling, entropy optimal sampling, because entropy is a very expensive resource, and they care about limited precision for theoretical guarantees. And people are also designing hardware architectures for sampling these trees, so the probabilities that we synthesize can be directly encoded into these hardware circuits to get optimally efficient, optimally accurate FPGAs, for example, for sampling. And there's lots of related work, which I'll just leave here on the slide. In follow-on work, we've looked at the problem of exact sampling with near optimal entropy. So the precision now is variable but linear, unlike the Knuth-Yau, and we pay a little cost. And then there's lots of other sort of assumptions that people have been studying for sampling, where the source may be biased or unknown, or the precision may be variable. And so I'll just leave that up here for people who are interested in sort of some of the other questions for sampling optimally that people are looking at. That's all. Thank you.
Questions? Thank you very much for the great talk. I really like it because of the interesting interplay between the floating point and the probability. And my question, I have 2 questions. The first one is that when you analyze the accuracy of your work, your algorithm, did you, consider the floating point rounding errors? If you did so, then at which point did you care about the rounding of errors, and at which point you didn't? And the second question is, did you, think about extending this work to continuous probability distribution. And yeah,
Yes, thank you. So the first question is, when we're computing the relative errors of our samplers, the answer is we chose baseline distributions where we can compute in closed form what is the target distribution of those samplers. And so these are, we used to compute the errors themselves an arbitrary precision arithmetic library that's using fractions. So we're trying to be as accurate as possible because obviously that's important, and part of the spirit is we want to use limited precision. So we analytically derived the actual target distribution of each baseline, and then we used an arbitrary precision library to find the relative errors. That's a great question. And then extensions to continuous distribution is a great question, and I think that's very naturally the next place we want to go. I think two things are needed. One is a precise semantics for this, because normals and Gaussians and all this kind of stuff have both irrational values on the x-axis and also irrational values on the y, because these are irrational continuous numbers with continuous PDFs. So there's like this design question for how do I discretize that? And we're definitely looking into that as future work.
We have one question from Slido. How does pseudo-randomness influence the sampling?
100%. So for our specific application, we're assuming that pseudo-random effects are not we're assuming we have perfectly accurate samplers. Now, for the hardware, they actually do have, perfect bit generators, and that's why in cryptography they want very efficient samplers. Now, the question for a PRNG, it's true that these are all pseudo-random numbers, but we're assuming the source is, we're living with the PRNG.
Yeah. So I may have just missed this slide, but is there some kind of a bound? Like if I know my distribution has some entropy and I'm going to chop off a tree at k bits, then I can say my distance is going to be so big?
Yeah, absolutely. So roughly here in the appendix, we're sort of looking at this question, which is like, what if I just want to truncate the probabilities up to a certain amount? Can I say anything about the error? And the answer is that depending on your choice of error metric, the errors can fluctuate enormously. So if you're choosing L1, that should be fine. But if you're looking at KL divergence, that could be very problematic, because if you miss an outcome, your error is going to be infinite. So if you want to use this for importance sampling, for example, or other applications, you want to make sure that your error metric is sort of being sensitive to how you truncate. And so that's, I think, a very important question.
Okay, let's leave it at that, and thank Feras again.
Thank you.
And the next session is in 10 minutes, the business meeting.